Now we will derive normal shock wave relations. Look at the figure. In the figure we have drawn normal shock wave. This is ahead of the shock wave and this is behind the shock wave. We know all the properties ahead of the shock wave, which are P1, T1, ρ1, U1. U1 is the speed of a normal shock wave, U1 at which it is traveling, and the observer is on the shock wave, so he will see the flow ahead of the shock wave coming at him at a speed of U1, and the ahead of the shock wave, the flow is supersonic. The flow is supersonic, and this is behind the shock wave, meaning it is a flow which has undergone the normal shock compression, and behind the shock wave the properties are P2, T2, ρ2. As we have seen in our example number 1, behind the shock wave pressure increases. So P2 is greater than P1, T2 is greater than T1, and ρ2 is greater than ρ1. But in the last example, example number 2, we saw that the flow behind the shock wave is subsonic. So its speed u2 is less than u1. Now all the properties of the flow ahead of the normal shock are known to us, and we have to determine what will happen to the properties of the fluid behind the shock wave, meaning we have to find P2, T2, ρ2, U2, and what will be the Mach number behind the shock wave. And these properties will be determined from the governing equations. So these are 5 governing equations we saw earlier. The first one is continuity equation. The second one is momentum equation. In the continuity equation, we have assumed that A1 is equal to A2. Its area is constant throughout the duct. Second equation is momentum equation. The third one is energy equation. And we have assumed that the whole process is adiabatic. Remember that the process will not be isentropic, because whatever happening inside the normal shock is irreversible. And that is why we can assume that the process is adiabatic but not isentropic process inside the normal shock wave. This is the equation of state, and the last equation is H equal to CPT, which is true for calorifically perfect gas. Now we will solve this equation and will determine the properties behind the normal shock wave. In determining these properties, we will first derive what is known as Prandtl relations. Prandtl relation, which is A star square is equal to U1 into U2, and after that we will find properties behind the normal shock in terms of different ratios, P2 by P1, T2 by T1, ρ2 by ρ1, T02 by T01, P02 by P01, etc. So in the first step, what we will do, we will divide momentum equation, which is equation number 2, with continuity equation, which is equation number 1. So we will get, and after dividing and rearranging different terms, we will get P1 by ρ1 U1 minus P2 by ρ2 U2 equal to U2 minus U1. Now we know that A square is equal to gamma P by rho. A square is equal to gamma P by rho. So from here we can find what is P by rho. P by rho will be A square by gamma. So in the first term P1 by rho 1, we will replace it by A1 square by gamma into U1 minus A2 square divided by gamma into U2 equals U2 minus U1. So what this equation represents? It is nothing but a combination of the continuity equation and momentum equation. Now consider an alternative form of energy equation that we have already derived, which is A square by gamma minus 1 plus U square by 2 is equal to, if you do not remember this equation, again go through that lecture where we derived alternative forms of energy equation A star square. So we can write this equation for position 1 as well as we can write this equation for point 2. So for 1 it will become A1 square U1 square and A star square. For 2 it will become A2 square upon gamma minus 1 plus U2 square by 2 equals gamma plus 1 by 2 into gamma minus 1 A star square. For 1 A star and for 2 A star will be same because our flow is adiabatic throughout. Though it is irreversible inside the normal shock, but it is yet an adiabatic flow, and A star for an adiabatic flow is constant throughout the flow. So from these two equations, we can find what is A1 square and what is A2 square, and we can substitute these values, this equation. So our A1 square will become gamma plus 1 by 2 A star square minus gamma minus 1 by 2 U1 square. Our A2 square will become gamma plus 1 by 2 A star square minus gamma minus 1 by 2 U2 square. We will put this A1 square and A2 square in our equation number 1. By putting it and by simplification, we finally get gamma plus 1 by 2 gamma U1 into A star square minus gamma minus 1 U1 square divided by 2 gamma U1. So by simplification of this equation, we will get gamma plus 1 by 2 gamma A star square divided by U1 U2 equals 1 minus gamma minus 1 by 2 gamma, which is nothing but gamma plus 1 by 2 gamma. Finally, we get A star square by U1 U2 equals 1, which is nothing but A star square equals U1 U2. And this equation is called, or this relation is called Prandtl relation. And this is an intermediate relation for normal shocks. Prandtl relation was A star square is equal to U1 U2. We will now derive relation between M1 and M2. We can write Prandtl relation as A star by U1 equals U2 by A star. We know that U1 by A star is M1 star, M1 star, U2 by A star is M2 star. Now we have derived relation between Mach number M and characteristic Mach number M star in earlier lectures. So let me write down what was the relationship. So M star square equals gamma plus 1 M square by 2 plus gamma minus 1 M square. And we will use this equation and put M1 star and M2 star. What is M2 star? M2 star will be gamma plus 1 M2 square divided by 2 plus gamma minus 1 M2 square equals 1 divided by M1 star. So what is M1 star? Gamma plus 1 M1 square divided by 2 plus gamma minus 1 M1 square. By simplification, we can find out M2 square is 1 plus gamma minus 1 by 2 M1 square divided by gamma M1 square minus gamma minus 1 by 2. You have to remember this equation M2 as a function of M1. You also have to remember this relation between M and M star. So from seeing this equation, we can say that Mach number behind the shock, which is M2, is a function of only the Mach number ahead of the shock, which is M1. So M2 is only a function of M1. Suppose that M1 equals 1, this will imply M2 equals 1, 2. It is nothing but infinitely weak shock. It is also called Mach wave or a sound wave. Suppose M1 tends to infinity, what will happen to M2? From this equation you can find out what will be M2. So M2 will tend to gamma minus 1 by 2 gamma, which is 0.378 for gamma is equal to 1.4. Now we will determine different property ratios. First one is density ratio, ρ2 by ρ1. Now from continuity equation we know that ρ2 U2 is equals ρ1 U1. So ρ2 by ρ1 is U1 by U2. Now multiply and divide this equation by U1. In the numerator U1 square, denominator U2 U1. We know from Prandtl relation that U1 into U2 is A star square. From Prandtl relation, we know that A star square is equal to U1 into U2. So what will be our ρ2 by ρ1? It will be U1 square. It will be U1 square upon A star square, which is nothing but M1 star square. And we know the relation between M star and M. From this equation we can write ρ2 by ρ1 equals gamma plus 1 M square divided by 2 plus gamma minus 1 into M1 square. So this is the ratio of densities ρ2 by ρ1. Now we will find out pressure ratio. P2 by P1. We will consider momentum equation, which is P1 plus rho 1 U1 square equals P2 plus rho 2 U2 square. This implies P2 minus P1 equals rho 1 U1 square minus rho 2 U2 square, and we know that rho 1 U1 is equals rho 2 U2. We can take common rho 1 U1 square. Inside we will left with minus rho 2 U2 into U2 divided by rho 1 U1 into U1. We know that rho 2 U2 equals rho 1 U1. So this will cut out. This equals rho 1 U1 square 1 minus U2 by U1. Now we know that A1 square equals gamma P1 by rho 1. This implies rho 1 equals gamma P1 by A1 square. And also U2 by U1 equals rho 1 by rho 2. And this relation we have written down from continuity equation. Put rho 1 equals gamma P1 by A1 square in this equation and U2 by U1 in this equation. So finally we will get minus P1 equals gamma P1 into U1 square by A square inside the bracket 1 minus rho 1 by rho 2. And we know that what is rho 2 by rho 1 from this equation. So we can write down it will be gamma plus 1 into m1 square divided by 2 plus gamma minus 1 m1 square. This equals gamma P1 into m1 square. By simplification we get 2 m1 square minus 2 divided by gamma plus 1 m1 square. Now take this P1 on the left side, so we will get P2 minus P1 by P1 equals 2 gamma divided by gamma plus 1 into m square minus 1. Remember this equation. This is a definition or this is a value of what is known as shock strength. Shock strength, which is defined as P2 by P1 minus 1. Remember, this has been asked. Finally, what will be P2 by P1? P2 by P1 will be 1 plus 2 gamma upon gamma plus 1 inside the bracket m square minus 1. So this is the pressure ratio. Next, we will find out temperature ratios. Temperature ratio T2 by T1 occurs the normal shock wave. We have already derived density ratio rho 2 by rho 1 and pressure ratio P2 by P1. Now from the equation of state, which is P equal to rho RT, we can write down P2 by P1 will be equal to P2 by P1 into rho 1 by rho 2. So what will be T2 by T1? We know P2 by P1, which is 1 plus 2 gamma upon gamma plus 1 into m1 square minus 1. And what is rho 1 by rho 2? It is 2 plus gamma minus 1 m1 square divided by gamma plus 1 m1 square. Remember that You should at least remember this equation P2 by P1, because in general we use this pressure ratio P2 by P1. So now we have derived M2 and other ratios P2 by P1, Rho2 by Rho1 and T2 by T1 as a function of M1 and gamma. So what is given? Given is M1 and gamma are given, and properties ahead of the shock wave, and we have to find out or obtain M2 Rho2 by Rho1, U2 by U1, P2 by P1, T2 by T1, and these all terms are functions of M1 and gamma. And lastly, I will make a note that all these relations that we have derived hold good for Mach number M1 less than 5. Mach number M1 less than 5, because M1 greater than 5 represents hypersonic flow, and the temperature behind the normal shock becomes high enough that gamma will no longer be constant. Gamma beyond M1 greater than 5 will no longer be constant, and that is why our equations are valid for Mach number M1 less than 5. And if M1 equals 1, then these all terms will also become 1. And as we have seen earlier, this is a case of Mach wave. Mach wave, we can also say it's a sound wave, or we can also say it is an infinitely weak normal shock. Now, we will apply second law of thermodynamics to our problem normal shock wave. We have derived relation between M1 and M2, and this is the equation of that. This equation holds for both M1 greater than 1 as well as M1 less than 1. Now, from the second law of thermodynamics, we will prove that it holds a physical meaning only for M1 greater than 1. It holds the physical meaning only if M1 is greater than 1, and it will not have any meaning for M1 less than 1. So, what is second law of thermodynamics? We know that S2 minus S1 equals Cp ln T2 by T1 minus R ln P2 by P1. Now we have already derived what is T2 by T1 and what is P2 by P1. So now let me just put these values quickly. So this is our equation of S2 minus S1 delta S, which is a function of M1. It is a function of M1. Now if M1 is equal to 1, then our S2 minus S1 will become 0. If our M1 is greater than 1, then S2 minus S1 will come out to be greater than 0. And if M1 is less than 1, then our S2 minus S1 will come out to be a negative value. And since we know that from the second law of thermodynamics, S2 minus S1 must be greater than or equal to 0, hence M1 less than 1, and this is an impossible case. So we have proved that for normal shock wave to occur, M1 must be greater than 1. I am repeating again. For normal shock wave to occur, M1 or Mach number ahead of the wave must be greater than 1. Now we will see why delta S is greater than 0. We have earlier seen that across the normal shock wave, pressure and temperature suddenly change, which means across the shock wave, pressure and temperature gradients are very high, and we cannot neglect viscous forces as well as heat conduction inside the normal shock because of high pressure gradients existing inside the normal shock wave, and these both are dissipative effect, and which in turn makes the whole process irreversible, and therefore our delta S will be greater than 0. That means the process is non-isentropic. We can say that it is an adiabatic, but we cannot say it is an isentropic process. Now next we will consider the effect of a normal shock wave on total pressure and total temperature. Now we will see the effect on total pressure and total temperature across the normal shock wave. Now let us first consider energy equation, which is H1 plus U1 square by 2 equals H2 plus U2 square by 2. We know that H1 plus U1 square by 2 will become Cp into T naught 1, and H2 plus U2 square by 2 will become Cp into T naught 2. This will imply T naught 1 equals T naught 2. So what does it tell us? Total temperature remains constant across the normal shock wave. Now to find out effect on total pressure, we know that there is some irreversible process going on inside the normal shock, which is viscous forces are present inside the normal shock, and we know that whenever there are viscous forces present, the total pressure will decrease. Remember, whenever there is some irreversible processes going on, such as friction, then total pressure will decrease. We will prove it mathematically. Now let us consider S02 total enthalpy minus S01 total enthalpy at 1. Now we know that the process ahead of the shock wave is isentropic. S01 will be equal to S1, and the process behind, or the whole flow behind the shock wave will be at S02 equal to S2. Therefore S02 minus S01, we can write it as S2 minus S1, and we know that S02 minus S01 will be equal to Cp ln T02 by T01 minus R ln P02 by P01, and we know that T02 equal T01. That means this term will be 0 because ln 1 is 0. Therefore S2 minus S1 will be equal to minus R ln P02 by P01, and from this equation, since S2 minus S1 is greater than 0, therefore minus R ln P02 by P01 will also be greater than 0. This implies that P02 must be less than P01. P02 must be less than P01, and this says us that total pressure total pressure decreases across the shock wave, across the normal shock. This ends the topic normal shock wave. Next, we will consider a question, and this question was asked in IAS 2010. The question is, for normal shock wave, derive the following expression. Derive the following expression: Pay upon Px equal to this, where x and y are the conditions before and after the shock wave. Here y stands for zero point 0.2, x stands for zero point 0.1, and we have to derive equation for P naught 2 divided by P1. P naught 2 divided by P1.